Let's now look at some applications of the dot product. The first one, which is quite useful, is finding the angle between two vectors. And that's just a rearrangement of our dot product formula, and we can get the cosine of theta is u dot v over the magnitudes multiplied together. So an example of that, if we wanted to find the angle between these two particular vectors, then the dot product, so 1 times -4, 2 times 2, 3 times 1, over their magnitudes multiplied together. So square root of 1 squared plus 2 squared plus 3 squared times square root of 4 squared, 2 squared, and 1 squared. We end up with 3 on 7 root 6, and so that angle would be approximately 80 degrees. Now, vector projections is something we looked at in 2D, but of course we can do it in 3D as well whenever we want to project one vector onto another. And here was our formula. So if we want to project the vector u onto the vector v, so it's u dot v over v dot v, that will give us a scalar, and then that scalar is times the v, so that'll get in the direction of the vector v. Now the length, if we just want the length, well, the formula is slightly different with the length. So we'll get u dot v, that's still on top, but on the bottom now is just the magnitude of v. So let's work that out. U dot v, so 4 times 2, 5 times -2, -3 times 1, over magnitude of v, square root of 2 squared plus 2 squared plus 1 squared, and we get minus 5 on 3. Now if we had to find the actual projection itself, so back to our original formula, so u dot v over v dot v, that gets us the scalar multiple of the vector in which we're going to project it onto. So u dot v will be 2 times 1 plus 3 times 1, and then minus 4 times 2. And v dot v, well, that's the same as the magnitude squared. So 1 squared plus 1 squared plus 2 squared, and we multiply that by the vector v. So we end up with 3/4 I plus 3/4 j, and then 3 on 2 k. Now we can also use this projection idea to find the perpendicular distance from a point to a line. Now obviously in 2 dimensions we have our perpendicular distance formula, but that doesn't work quite as well in 3 dimensions because of the nature of equations of lines. So let's look at it using vectors. So here's a diagram. We're going to find the distance from P to the line or the vector Mn. So MQ, the vector MQ, will end up being the projection of the vector P onto Mn. Now MQ, another way I could do that, would be the vector MP plus the vector PQ. Rearranging, we get that the vector PQ is MQ minus MP. Now MQ, that's our vector projection of P onto what I've called the vector N, minus the vector that we're projecting, so P. So the distance then would be the magnitude of that result. So the magnitude of the projection of P onto N minus P itself. So let's do this example. We're going to find the perpendicular distance from the point 1, 0, 2 to the line or the vector joining 2, 2, 1 and 3, 1, 1. So I'm going to let P equal the vector BA. So I'm joining the point to one of the ends of this line. So I could have chosen C, I've gone with B. So vector BA, head minus tail, would be minus I minus 2j plus k. We're also going to need the vector that we're projecting it onto, and so that's BC. And again, head minus tail. In this case, we just end up with I minus j. So we want the magnitude of the projection of my vector P onto the vector U minus the original vector P itself. So when I do my calculations, the projection of P onto U ends up being a half of I minus j. And from that, we're taking away what we worked out P to be. So minus I minus 2j plus k. Tidying that up, 3 on 2i plus 3 on 2j minus k. That's what we want to find the magnitude of. So 3 on 2 squared plus 3 on 2 squared and 1 squared, square root of all that, we end up with root 22 on 2 units. So this time I'm going to do a traditional geometry question where we have a triangle and we want to classify what type of triangle it is. We've been given the coordinates for the 3 vertices. So it's not on the XY plane or the YZ plane or the XZ plane. It's these 3 points are out in space somewhere, but it would still create a triangle. So all right, let's find vectors for each of the sides. So AB, head minus tail, we get 3, 2, 1. BC is minus 2, minus 2, minus 2. And CA is minus 1, 0, 1. Now, classify triangles. We can classify them based on sides, or we could look at the angles inside the triangle itself. Probably quicker to work out the length of each of these vectors. So AB works out to be square root of 14, BC square root of 12, CA is square root of 2. So all right, well we know it's a scalene triangle. Mind you, I notice 12 and 2 add up to be 14. So it actually satisfies Pythagoras' theorem. So CA squared plus BC squared is AB squared. So we got a right angle triangle. So that's using the sides. If I'd use the angle, then I'd find the dot product between all of these. And well, I know it's going to end up being a right angle triangle, but once I've done my dot products, I would have discovered that one of them would have been 0. And remember, dot product equaling 0 means that the vectors would be perpendicular. Now, I'm going to cheat a little bit here because I know where the right angle is. So magically, I'm going to hit on the right one straight away. BC.CA, well, what do you know? It turns out to be 0. So therefore, I know the vertex C is a right angle. So BC is perpendicular to CA. And again, that tells me it's a right angle triangle. In reality, if I hadn't found the sides, I would find each of those dot products until I hit on one to be 0. Okay, now I'm going to do a three-dimensional problem. You may recall last year we did some 3D trig, but instead of using those ideas, we're going to use vectors to solve our problem. So we've got a square pyramid. Bases are 2, V is a vertex. The pyramid is symmetrical. That basically means the vertex is sitting immediately above the center of the square base. So let's draw a picture. Well, I'm going to place it onto our Cartesian space. So I'm going to have the base of our pyramid sitting on the XY plane, and I'm going to center it at the origin, and then that way the vertex will be on the Z axis. So there's my pyramid. Now they've given me some dimensions. I can work out that one of the corners of my base is 110, because they told me the base was of 2 units. So if I've set this up symmetrically, there would be 1 unit either side of the x-axis, either side of the y-axis. The vertex is 4 units, so I'll give that coordinates 0, 0, 4. Now joining those 2 points up creates a vector. It would be the vector, head minus tail, and for this one the head is the vertex. So u is -1, 4. All right, we want to find the angle that this slant edge makes with the base. So I need to join 110 to, well, I'll join it to the center. I mean, I could have also joined it to the opposite vertex, but I mean, 0, 0, 0 is a much easier number to work with. So that vector I've drawn in would be -1, 0. And we essentially want to find the angle between these 2 vectors. So we'll use our cos theta is u dot v over the magnitudes multiplied together. So u dot v will get -1 times -1, and then -1 times -1 again, and 4 times 0 over the magnitudes. So square root of 1 squared plus 1 squared plus 4 squared times the square root of 1 squared plus 1 squared plus 0 squared. We got 2 on root 36, which simplifies down, and working out theta. Now, another geometry problem. We're going to prove that the medians of a triangle meet at a point, and that point divides each median in the ratio 2 to 1. So here's a triangle. I've made one of the vertices the origin, now just to make life a little bit easier. So I'm going to define two vectors here. OA, the position vector, because I've made one vertex the origin, and similar with B, so I'll call those vector A and vector B. A median is a line that joins a midpoint to the opposite vertex. OX would be half of the vector OA because X is the midpoint. Similarly, Y is the midpoint of OB, so the vector OY is a half B. So I'm going to draw in the two medians coming from those points. I'll also join up O to Z, and that'll be just the vector Z, because again it's coming from the origin, so I'll call it the position vector Z. Now that point Z is going to divide BX in the ratio M to N. I could have just as easily chosen AY because they're both medians, and we want to show that that ratio is 2 to 1. All right, so the ratio of AZ to ZY I'm calling M to N. Cross multiply. Now vector AZ is head minus tail, so Z minus A. Same with ZY, we'll get B on 2 minus Z. M plus N, a bit of a rearrangement here. I want to make Z the subject. So M plus NZ is NA plus MB on 2. Remember I said I could have just as easily have picked the median AY to do this. Now if I had chosen AY, then I would have ended up with M plus NZ was NB plus MA over 2. And the working out is exactly the same. Well, if they're both equal to M plus NZ, then they must equal each other. So I now know that NA plus MB on 2 is equal to NB plus MA on 2. Remember, we're trying to find the ratio M to N. So if I group the M's together, I'll get M on 2, B minus A. Group the N's together, I'll get N outside of B minus A. Well, I can divide both sides by the vector B minus A. And we get M on 2 equals N, so M on N is 2 to 1. And that's the ratio we were trying to prove. All right, so we'll look at exercise 5D and 5E using vectors to solve some traditional problems.